Hello. In this video, we are going to prove the following theorem. No group has exactly two elements of order 2. Now, the approach we're going to take to prove this is we're going to suppose that we have a group and we know of two elements in that group with order 2. From there, we're going to show that we can always find a third element in that group with order 2. So let's consider a group G with identity element E, and let's suppose that A and B are distinct elements of G with order 2. From here, we're going to show that we can always find a third element in G with order 2, so that it's distinct from A and B. Now, since the order of A and B are equal to 2, this means that A squared is equal to the identity, B squared is equal to the identity, and if we take this equation and multiply the inverse of A on both sides, we get that A is equal to the inverse of A. If we multiply this equation, both sides, by the inverse of B, we get that B is equal to the inverse of B. Some other facts that are going to be useful is showing that AB is not equal to the identity, AB is not equal to A, and AB is not equal to B. So then, what goes wrong if AB is equal to the identity? Well, if AB is equal to the identity, then if we multiply the inverse of B on the right side of both of these expressions, then we get A is equal to the inverse of B. But the inverse of B is equal to B, so this shows A is equal to B, which contradicts the fact that A and B are distinct. So we can't have AB equal to the identity. So then, what goes wrong if AB is equal to A? If this happens, then AB is equal to A times the identity. So by the cancellation law for groups, we can cancel out the A's. So we get that B is equal to the identity. But the identity element has order 1. So this contradicts the fact that B has order 2. So we can't have AB equal to A. And now, what goes wrong if AB is equal to B? If AB is equal to B, then AB is equal to the identity times B, so by the cancellation law, we can cancel out the B's, so we're left with A is equal to the identity. But the identity element has order 1, so this contradicts the fact that A has order 2. So we can't have AB equal to B either. So we have shown that AB is not equal to the identity, AB is not equal to A, and AB is not equal to B. Now remember, the whole goal is to show that we can always find a third element in G with order 2. And to show that, we're going to split this up into two cases. Either A and B commute, or they don't commute. Let's first consider the case where A and B commute. The claim is, in this case, we can show that AB is a third element of G with order 2. And to see how that happens, we'll notice if we raise AB to the power of 2, well then, this is just AB times AB, but since A and B commute, we can replace the BA in the center with AB, so this is just AA, BB, but we know that A times A is equal to the identity, and B times B is equal to the identity. So this is just the identity times the identity, and by definition of the identity, this is just equal to the identity, and this shows that AB to the power of 2 is equal to the identity. So we see that there exists a positive integer such that if we do AB to the power of that positive integer, we get the identity. This tells us that AB must have finite order. And remember, the order of AB is the smallest positive integer that's able to do this. Therefore, the order of AB must be less than or equal to 2. But since the order is a positive integer, this means that the order of AB is equal to either 1 or 2. So then, why can't the order of AB be equal to 1? Well, remember, the only element with order 1 is the identity element. But since AB is not equal to the identity element, that means the order of AB can't be equal to 1. But since the order of AB is equal to either 1 or 2, but not equal to 1, we must have the order of AB is equal to 2. So this shows that the order of AB is equal to 2, but remember, we want to show that AB is a third element of G with order 2. In other words, we want to show that AB is distinct from A and B. But wait a minute, we already know that AB is distinct from A and B, so this shows that AB is a third element of G with order 2. And so, this completes the case where A and B commute. Now let's consider the case where A and B don't commute. The claim is, in this case, we can show that AB A inverse is a third element of G with order 2. So then what happens if we raise AB A inverse to the power 2? Well, this is just AB A inverse times AB A inverse. Now we know that the inverse of A times A is just equal to the identity element. So we get this, but then when we multiply by the identity, we know that the identity element is just going to go away. And then we know that B times B is equal to the identity. So this gives us A times the identity times the inverse of A. But then we know that when we multiply by the identity will go away. And then we know that A times the inverse of A is equal to the identity element. So this shows that AB A inverse squared yields the identity element. So we see that there exists a positive integer such that if we do AB A inverse to the power of that positive integer, we get the identity element. That tells us AB A inverse has finite order. And whatever the order of AB A inverse is, it's the smallest positive integer that's able to do this. Therefore, the order of AB A inverse must be less than or equal to 2. But we know that the order of AB A inverse is a positive integer, so the order must be equal to either 1 or 2. So let's eliminate the possibility that order of AB A inverse is equal to 1. To do that, all we have to do is show that AB A inverse is not equal to the identity element. So what goes wrong if AB A inverse is equal to the identity element? Well, if this happens, then if we multiply the right side of both of these expressions by A, then we get AB is equal to A. But this is false, because we know from earlier, we've shown AB is not equal to A. And so, we can't have AB A inverse equal to the identity. But remember, the identity element is the only element with order 1. So since AB A inverse is not equal to the identity element, AB A inverse can't have order 1. But since we know that the order of AB A inverse is equal to either 1 or 2, but it's not equal to 1, that means AB A inverse must have order 2. But now we want to show that AB A inverse is a third element of G with order 2. In other words, we want to show that AB A inverse is distinct from A and B. So what goes wrong if AB A inverse is equal to A? Well then, if we multiply the right-hand side of both of these expressions by A, we get AB is equal to A squared, but A squared is equal to the identity, so this shows AB is equal to the identity. But we know from earlier, we have shown AB is not equal to the identity, so this gives us a contradiction. So we can't have AB A inverse equal to A. So then what goes wrong if AB A inverse is equal to B? Well, if this happens, then if we multiply the right side of both expressions by A, we get AB is equal to BA. But this is false because we're working under the assumption that A and B don't commute. And so we can't have AB A inverse equal to B. So since the order of AB A inverse is equal to 2, and it's distinct from both A and B, this means that AB A inverse is a third element of G with order 2. And so we have shown, in either case, we can always find a third element of G with order 2. So putting this all together, we see, given any group G, if we know of 2 elements in G that have order 2, then we can always find a third element with order 2. So no group can have exactly 2 elements of order 2, because we can always find another one. And so this completes the proof. And so yeah, that's pretty much it for this video.